In this video, we are going to graph exponential functions and also state key features. If you remember from yesterday, our format for an exponential function is y equals a times b to the x, where a is the initial value and b is the multiplication pattern. We might also call this our exponential growth or decay factor. When we look at number 1 on page 5, we can see that we have an initial value of 1. Now, when I mean see like with our math eyes, 1 times 3 to the x, we have an initial value of 1. We have a multiplication pattern of 3, which tells us this is a growth. So 2 is asking us to graph g of x equals 3 to the x. So I'm going to make a table. I'm going to pick a few numbers that are positive, negative, and 0. So I'm going to go with -1, 0, 1, and 2. So I'm going to start at the bottom because that's the easiest, because 3 squared is just 9. 3 to the first is just 3. 3 to the 0 is 1. And then 3 to the -1 power, I want to remember, is 1 over 3 to the first, or just 1/3. So once I have these values, I can plot them on my graph. So I have 0, 1, 3, 1, 2, 9, and then I'm going to go with -1, 1/3 here. Now, if I were to add more negative numbers to my table, like let's say I evaluated -2, 3 to the -2 power would be 1 over 3 squared, or 1/9. And then to the -3 power would be 3 to the -3, or 1 over 3 cubed, which is 1 over 27. And you can see as I go further to the left on the x-axis, the denominator is going to increase by a factor of 3. It's going to get really, really small, but it's never going to get below 0, because I'm always going to have that 1 that I'm dividing by a number that is growing by a factor of 3. So I'm just going to, that's a little bumpy. Hopefully yours is a little straighter. I'm trying to go one more time. This should, well, it's not getting any better. Should look straight, and let's give it an arrow and an arrow. We want to make sure, because the graph kind of trails off here, we have a vertical, horizontal asymptote. Oh, it won't do me the dotted line. It's so sad. Yeah, so right here at this pink. Nope. Well, we're just going to have to eyeball it in. We have a horizontal asymptote here because the graph on the left side is approaching 0. We always want to make sure we dot that in. See, I'll make it a little longer as you can see it. We have a horizontal asymptote here. PTOTE, and it is y equals 0. Okay, so let's go to the questions at the bottom. Number 3 says, is the graph continuous? How do you know? Yes, it is continuous. How do I know that? It can be drawn with one pencil line. For now, that's going to be how we know if something is continuous. If I don't have to pick up my pencil to draw the curve, it's a continuous function. What is the domain? Well, the domain here is all real numbers, because as you can see in my table, every single value for x that I substituted, I could evaluate it. The range. Now, the range here is not going to be all real numbers. It's going to be y is greater than or equal to, or y is greater than 0, not equal to, just greater than. Whoops. Because we have all the y values above 0. As we move from left to right, we see that the graph increases. And as we move from right to left, as the x values decrease, what's happening, we can see that the y values are approaching 0. Number 8 is a fill in the blank. It says, since the graph of g of x equals 3 to the x approaches the x-axis, the line y equals 0 is called the horizontal asymptote, P-T-O-T-E. Okay. Okay, today we are going to graph more exponential functions using a table and then looking at the properties. So let's take a look at page 6. On page 6, we see something at the top and it says, what can we determine? Well, we can determine that again, we have an initial value of 1. And now our multiplication pattern is 1/3, so we know we have a decay. Because it's between 0 and 1. So go ahead, pause the video. Why don't you pause the video and try to fill in this table on your own. Let's go from -2 to 2. You should have tried to fill in this table on your own. The order you complete this in does not really matter. I'm again going to go from the bottom up. If I have 1/3 squared, I square the 1, I square the 3, and I get 1/9. Anything to the first power is itself, so I just have 1/3. Anything to the 0 power is just 1. Now, when I raise 1/3 to the -1 power, it's like raising its reciprocal to the first power. So we just get 3. Kind of out of space here. I'll do the -2 over here. If I have 1/3 to the -2 power, that's like 3/1 squared. Again, I take the reciprocal, then I square 3/1, which is the same thing as squaring 3, and we get 9. So go ahead, take a moment, jot down the arithmetic, pause the video if you need to, and graph the points. Again, on one side of the graph, we end up with 1 divided by a very large number, because like eventually this is going to be 1 divided by 3 to the 10th, which is pretty big. So it's going to get really close to 0 again on the right side versus the left side last time. So I'm going to put in that dotted asymptote. Please make sure you put in your dotted horizontal asymptote. Okay, questions at the bottom. Is it continuous? Yes. How do I know? I can draw this with one pencil. Like if I'll take my highlighter and I can highlight this graph without picking up the highlighter. Well, there, one line. So it is continuous. The domain, the x values, again, this graph stretches from left to right. So its domain is all real numbers. But again, I don't have 0 and I don't have anything below 0. So I'm going to say the domain is, or the range is y is greater than 0. Follow the graph from left to right. Well, now it's not increasing. Now, as I go from left to right, the graph's actually going down and it's approaching 0. If I go the opposite way from right to left, that's where they are increasing. So this actually means that the graph is decreasing as we move. Let's add that in our answer here. Okay, so like before, since the graph approaches the x-axis, the line y equals 0 is called the horizontal asymptote. All right, we're going to do 4 more graphs together, and then you're going to do 4 on your own for homework. So let's take a look at page 7. On page 7, we just have two equations and 2 graphs. And at first glance, they look really similar. Take a moment and identify the difference between number 1 and number 2. If you said that number 2 has a negative x, you're correct. And we're going to talk about that in just a moment. What can you determine? What is the initial value? And what is the multiplication pattern? The initial value is 2. And the multiplication pattern is 2/3, which is between 0 and 1. So again, we have another decay. I'm going to pick a few points here, not too many. So let's start with 0 is always a good choice. So if we do 0, we have 2 times 2/5 to the 0. Do I have more room at the bottom? I'm going to do my arithmetic at the bottom because I really don't have a lot of room in the graph. So our equation is y equals 2 times 2/5 to the x. Here we go. If we sub in 0, put the table right here so I can see it later. We sub in 0, so that's 2 times 2/5 to the 0. Well, 2/5 to the 0 is just 1. 2 times 1 is 2. Not surprising, that's our initial value. Now let's do 1. 2 times 2/5 to the first, it's just 2/5. So I'm going to put this 2 over 1, and I can multiply across, and I get 4/5. Now let's make this squared. I'm just going to change this. 2 times 2/5 squared is going to become 2. And again, I'm leaving this 2 over 1 because I'm going to multiply to a fraction. Square the 2/5. We get 4 over 25. So we get 8 over 25. And what's going to happen as I raise that power, it's going to get smaller and smaller and smaller. 4/5 is like 0.8. 8 over 25 is significantly smaller. Let's try some negative numbers. Let's do 2 times 2/5 to the negative 1 power. So that's going to take the reciprocal of the 2/5. So we're going to have 2 times 5/2. Well, that's pretty nice. And then 2 times 2/5 to the negative 2 is going to be like 2 times 5/2 squared is going to, well, 5/2 squared is 2 times 25 over 4. These reduce. 25 divided by 2 for graphing purposes is 12.5. And that's probably all we're going to be able to fit. So let's go ahead, bring our graph back up here. And we've got 0, 2. We've got 1 little less than 1. And then 2 is significantly smaller. And then negative 1 was 5. And then negative 2 is 11, 12, and a little bit. So again, we can see the graph is a decay graph. It's coming down. And again, if I put in bigger numbers, multiplying by, well, that came out good. Multiplying by 2/5 is going to make it get smaller and smaller. I'm going to dot in my asymptote. Okay. And we'll state some features. Once again, we have a domain of all real numbers. That's going to be an always for exponential functions. I don't even like this other one's exponential. Domain is all real numbers. Now, the range is not always y is greater than 0, but until we start transforming them, they will be. The y-intercept is at the point 0, 2. That's where the graph crosses the y-axis. And the asymptote it's approaching is y equals 0. When I look at number 2, the only difference is this negative power. So I have two choices. I can work with the negative power. My mouse. I can work with the negative power, or I can rewrite it. I'm going to rewrite it because it's going to tell me something about how my graph should look. So I'm going to write this as 5/2 to the x. Negative power, take the reciprocal, get rid of the negative. I still see I have an initial value of 2. But now I have a multiplication pattern of 5/2, which is larger than 1. So now I have a growth function. I'm not going to go through the arithmetic as slowly as I did the previous problem, but feel free to pause the video, try the arithmetic on your own is what you should do, and then check back with me. This is 2. This is going to be 5. This is going to be 25. This is 12.5. Now, -1, that's going to take it back to 2/5. This is going to become 4/5. And then this one will be times 2/5. It's going to be 8/25. So what we have here, because the negative is in the argument, it's up like where the function is. This is an exponential function, and the negative is up with the x. What we see for the first time really is a reflection over the y-axis. So when we put this in, like this equation is exactly like the previous one, except the negative in front of the x, and you can see it has reflected the graph of number 1 right over the y-axis. So that's a good example. Ooh, I missed. Make it bigger. Of a y-axis reflection. And got in our, that's pretty ugly, asymptote. Again, the domain is still all real numbers. We don't have anything below 0. 2 is still our intercept. Y equals 0 is still our asymptote. We have 2 more graphs, and these ones are going to have slightly stranger exponents, but we are going to be able to rewrite them so that it is y equals a times b to the x. So when we look at number 3, the first thing we notice is there's like this 3 with the x. I don't want that there. So I have to remember that when I raise a power to another power, I multiply the powers. So for example, if I had 5 squared to the 3rd, that'll be like 3 of those. And 2, 4, 6. So that's the same as 2 times 3 is 6. What I can do is I can kind of take that apart. I can think about this 3x as 3 times x. So I have 2 to the 3rd to the x, because think about it, 3 times x will give us this 3x. So what we find is that this multiplication pattern is actually 8, and the initial value is 1. So if I go to make a table for this, again, I got this because 3x can be rewritten as 3 times x. And then power to a power you multiply. It's like we're taking it apart. 2 to the 3rd is 8. I'm just going to do 3 points here because I don't think I'm going to fit more than that. This is going to be 1/8, 1 and 8. Got a nice growth function here. It's got a horizontal asymptote. It's got a domain still of all reals and a range of y is greater than 0. The y-intercept is only 0, 1, but the asymptote is still y equals 0. Again, today's focus is just make the table, put down the graph. What do you see? Number 4 is pretty similar. It's got that negative sign though. So I'm going to immediately make this 1 over 3 to the 2x. And then again, think about the 2x as 2 times x. So I can break this into 3 squared to the x, because 2 times x will become 2x. So what I really have here is 1 over 9 to the x. And because 1 raised to any power is still 1, I've got 1/9 to the x. The table for this one's going to be small also because I'm not going to be able to fit a lot. 0 is 1 because 1, and then, put a 0 here, and that's just 1 times 1 is 1. If I put in -1, it will flip the 1/9 over to 9. And if I put in 1, it's just 1 times 1/9. Go ahead, dot in your horizontal asymptote. And the properties for this one, unfortunately, because we're not really doing anything other than reflecting things over the y-axis, properties are the same. We didn't have an initial value other than 1, so the y-intercept doesn't change. Now you should work on page 9. You need to do this without a calculator, and I recommend highly that you create a table with at least 3 points. I need to see at least 3 points in your table, and answers are uploaded on our shared drive.